So the three previous videos that you've watched here are made or were made for the end of a Calc 2 class. It's the very last thing we do in our Calc 2 sequence. However, this is now the beginning of differential equations, so the content was appropriate, but some of the things I said are maybe not appropriate for the start of a differential equations class. So here's a few things I do want to say about separable differential equations now that we're actually starting to learn about how to solve differential equations. Okay. So first of all, we're dealing, for the first part of this course, with first order differential equations. So differential equations where the derivative of a function y can be written as some function of x and y. Okay. The highest order derivative that you'll see in these equations is first order. That is a first derivative, right? So that's what we call it, a first order differential equation. Now, one way to interpret these things, which was not mentioned at all in the previous videos, and is mentioned in chapter 1 in the textbook, but we're starting with chapter 2, so this is just a concept that I wanted to get out here, is the notion of a slope field or a direction field. I believe we're going to be calling it a slope field because we're not dealing with vectors at this point. But what we have is we can solve a first order differential equation like this, where dy dx equals some function of x and y. Then what it's telling us is that the solution curve has to pass through each point with a particular slope. And so what we're doing is we're showing that graphically here. So for instance, the graph shown here is for dy dx equals minus y over x. Sorry, minus x over y. This is, so for instance, at the point 2, 2, x is 2, y is 2, so dy dx is minus 1. And at that point, I put a little hash mark with slope minus 1. At the point 0, 3, where x is 0 and y is 3, the slope is 0, and so the little hash mark at that point has slope 0. At every point in the plane, you draw a little hash mark that just shows you what the tangent line, what slope the tangent line would have at that point. Now, if you plot this on a close enough grid where the points that you're plotting are all fairly close together, you can actually begin to see the solution curves because you're looking at a whole bunch of little tangent lines, or little tangent line segments anyway. And these are looking very circular. In fact, I do believe in a previous video we solved this one. If not, I do solve it down here, right? Find the solutions here where we separate it, get the y's on one side, the x's on the other side, integrate both sides. Yes, I'm sure I did this one. Right? And so you get things that look like x squared plus y squared equals a constant, which are circles. And sure enough, that graph looked like circles. Okay. Now, one of the things I want to point out is that the textbook here gives a little different definition of what a separable differential equation is. I like to think of it like this, where dy dx is a product of some function of x and a function of y, so then you can divide, or a quotient, right? It's some way that you can multiply and divide to get all the y's on one side and all the x's on the other side. The book says like this, where you got f of x plus g of x times dy dx equals 0, or they even multiply both sides by dx and write it like this. So f of x dx plus g of y dy equals 0. I mean, this looks a lot like what we're aiming towards, right? Because then you're going to take the y's and move them over to the other side, or take the x's, move them over to the other side. But anyway, you can get them separated into a function of x times dx equals a function of y times dy. One way or the other, however you define it, the goal is to get to the point where it looks like this. Right? This is what we're aiming for. So anyway, that's just the textbook. This textbook that we're using, the way it defines it is a little bit different, but they're all equivalent. Okay, so then I wanted to show a couple of examples here. We already did this one in a previous video. Here's another one, x y prime equals 1 minus y squared, square root of that. It is separable. I'm going to, well, first of all, I'll write the y prime as a dy dx, and then then what? So then I'm going to divide both sides by this stuff, and I'm going to divide both sides by x, and we end up with this. And so we get the integral, so we get this 1 over the square root of 1 minus y squared times dy equals 1 over x times dx. Integrating both sides now yields, what am I doing? Am I doing a trig substitution? Yeah, on that left side. This is a good review of calculus here. Calc 2, what are your integration techniques? You got to be able to integrate those both sides. This right-hand side is probably easy enough, but the left-hand side, do you know how to do that? Well, anyway, I do. So we got, with the 1 minus y squared, I'm going to let y equals sine t, dy equals cos t dt. Substituting in, there's the 1 minus y squared. The dy turns into a cos t dt, and then the denominator is cosine t, because 1 minus sine squared t is cos squared t, and take the square root. You get cosine t, cancel the cosine at the top, and you just get the integral of dt, which is t plus a constant, which is arc sine. So the left-hand side here integrates to arc sine. Maybe you recognize that, maybe you didn't. If you didn't, of course, you can just do this. The right-hand side is, of course, the log of the absolute value of x plus a constant, and then I can solve for y by taking the sine of both sides, and y is the sine of the log of x plus c. Okay. Notice that the plus c is inside of the sine. Now, a lot of times we do stuff to both sides. You know, if I multiplied both sides by 2, that would be 2 times c, which I would still say, that's just a constant, right? So I just have plus c on the end where instead of plus 2c. But in this case, sine does not distribute over addition. The only thing that distributes over addition is multiplication by a constant. So, so this is the sine of the log plus c, and the plus c is inside the parentheses, and you can't pull it out. All right, another one here. Initial value problem. So here's a differential equation with an initial condition. So when x is 1, I want y to be -2. Separating, I can multiply both sides by y, and I can multiply both sides by dx to get this. Integrating both sides gives me y squared over 2 on the left, x minus x squared plus a constant, right? Again, there's a constant on both sides, but get them together to be just plus c on one side. And then plugging my initial condition in. So for x's, I'm replacing them by 1s, and for y, I'm replacing it by -2. I get that c is 4. And so y squared is this. Now, I would be inclined to leave it like this, but quite often you will see solutions written in terms of y equals, so explicitly, right? Whereas as written like this, it's an implicit equation. It's a relation between x and y, where this is y is a function of x. Now, the thing you got to be careful of here is you could take the square root, but with y being negative for my initial condition, I need to take the negative square root. So this is, the graph of this thing is an ellipse or something like that. And you could have the top half of the ellipse or the bottom half of the ellipse, but the initial condition was on the bottom half of the ellipse. And so we have to take that function, which is describing the part of the curve that passes through the initial condition, which is the negative square root of x here. Okay. So when you do that, when you solve for y, make sure you solve for y in a way that's meaningful to what initial condition you have. Now, let's see. Do I have one more example? Actually, this example I think we already did in the other video, but I put it here just for reference. This is one of my favorite, just basic standard differential equation that's not just derivative, y prime equals some function of x. It's y prime equals y. Can you come up with a function whose derivative is equal to the function itself? Now, this is one that students generally can say, e to the x works that way, doesn't it? Yes, but then it's like, are there any others? Any other functions that when you take their derivative, you get the same function back again? And the answer is yes, there are. And let's see if we can find them all. Right? So this is just dy dx equals y. If I divide by y and I multiply by dx, I get this equation right here. Integrating both sides, natural log of the absolute value of y equals x plus a constant. So the absolute value of y equals e to the x plus c, which we write that e to the x plus c as e to the x times e to the c. And then just as we did in previous videos, e to the c is a positive constant, but it's a constant. And if I write it as c, then that constant could be positive or negative, which allows us to get rid of that absolute value sign. And what we get is that y is some constant times e to the x. What are all the functions that satisfy the derivative of the function is equal to themselves? Well, they're all just a constant times e to the x. So 7e to the x, if you take the derivative, you get 7e to the x. Turns out there aren't any others. Those are the only ones. Everything that satisfies that differential equation looks like some constant times e to the x. Okay, so there's our introduction to separable differential equations. Of course, if you have any questions, please ask them in the discussion section, the discussion forum, and or send me a message. Right?